All right, so graphs of inverses. This is something that you should have been introduced to in Algebra 1, okay? But we're gonna dive into it and kind of reiterate some of the things you learned in Algebra 1. We're on the notes. Yes. All right, so steps to graph the inverse. These should be at the top of your notes. Yes, no, maybe so. Okay, so first thing you're gonna do is you're gonna create a table of values in table 1 for the equation. To create a table of values, we're just plugging, we're deciding on some x values, plugging them in, and getting our y values, right? Then we're gonna plot the points. We're gonna switch our x and y to create our second table. We're gonna plot those points in graph. And then we're going to draw in our line y equals x on the graph as our dashed line. And we're going to have a conversation from there. Okay? Does it sound doable? All right. It is. So we have y equals 2 to the x. What kind of function is this? An exponential, an exponent. There's an exponent. A variable is an exponent. So therefore, this is an exponential function. Agreed? Okay? So for exponentials, we know that we're either going to be a growth or a decay, right? Looking at our problem here, looking at our equation here, what do we have? A growth, because it's greater than 1. Yeah? All with me? Okay. All right. So table. The values of your table are totally up to you, but I usually choose the smallest values. So I'm going to use -2, -1, 0, 1, 2, and 3 as my table values. Okay, and now we have to do what? Plug them in. So let's do it out loud. If I substitute in -2 for x, what is 2 to the -2 power? Oh, what did you say? Well, it's a quarter, 1/4. Yes. I didn't hear what you said. It's not what I wanted you to say. Okay. What we have to remember is that when you have a negative exponent, that means that it belongs in the denominator. It's been a bad number, and it goes in the denominator, so it can become a good number. Okay. So when you have a negative exponent, that means it actually belongs where? In the denominator. So 2 squared is 4, but 2 to the -2 is 1/4. Okay. All right, so now we have -1, so it becomes 2 to the -1. So 2 to the 1 is 2, but it's negative, so it's 1/2. Yeah, that's what we're doing. You want me to write it? We did 2 to the -2, then we did 2 to the -1. So this means that we have 1/2 squared. So 2 to the -2 means we have 1/2 squared. And 2 squared is 4. Like that? Got it? We're taking it from being bad to being good. 1. And that's because the rule for 0 is anything to the 0 power equals 1. All right, now we're back to positive numbers. And it's just 2 to the 1. What is 2 to the 1? 2 squared. 2 to the 3rd. 8. These are the points that we're going to plot. So you shouldn't need me to plot. So go ahead and plot your points and create your graph. It doesn't exist. It's an asymptote. It's a boundary line. Yeah. All right. So right now we're all plotting our points. Did it come out to be a growth like we said? Yes. Now, next thing you got to point out is that there is a boundary line. Does anyone remember what a boundary line is called for the exponential function? An asymptote. There's an invisible boundary line that's why it's above. It never ever is going to touch. It'll get us. It'll be 0.000001, but it'll never be 0. I just that notice I'm telling you about to tell you why. Okay. Now the reason why this is happening is because what did we say a negative power does to the number? It means it's a fraction, right? So a negative power means it's a fraction. And if I look at this fraction, the denominator is going to keep growing, but what's happened to the numerator? It stays the same. So it's like I have $1 and now I'm sharing this dollar with one person. Now I'm sharing this dollar with 2 people. Now I'm sharing this dollar with 4 people. Now I'm sharing this dollar with 5 people. I'm going to keep sharing this dollar, but the value of the dollar is going to do what for each person? Keep shrinking, right? It's going to keep going down and down and down and down. And that's what this asymptote represents. Okay. I still have that dollar that I'm trying to share with everyone, but everyone's going to end up getting very little and have no meaning, right? Yeah, all exponentials have a boundary line. For this one, it's 0. No, they're not all 0. All right, so we're at X, not X. I wrote X. That should be Y equals 0. Lo siento. Okay, so now looking at this graph, let's talk about what is happening with Y. What is its domain? From left to right, what's happening? All real numbers. Our domain is negative infinity to positive infinity. It goes forever to the left and forever to the right. So our domain is negative infinity to positive infinity. But what is our range? 0 to positive infinity. I want to get as close to 0, but I'm not going to ever touch 0. No, yeah, so it would be strictly greater than 0. So if you wanted to write it as that, it would be Y is greater than 0, but not equal to 0. The other way of showing that, instead of using a bracket, we use a parenthesis. Okay. All right. So that's our original given function. Got it? All right. Now, our second table is going to represent what's called its inverse. So our second table is going to be... Oh, I did not in this period. I'm so sorry. Yes. If you have a pen or pencil of a different color, we need that transition. Or trade with the neighbor. All right, so inverse. So when we're creating an inverse, we're going to write it as y to the negative 1. It is not a power, it means inverse. So if I see y to the negative 1 or f of x to the negative 1, that is telling me I have the inverse, or it wants me to find the inverse, okay? All right, to find the inverse, all you're doing is switching your x's and y's. So for example, negative 2, 1, 4 becomes 1, 4, negative 2. Are you with me? And it's going to do for all of them. And that's how you find your inverse of the table. Yay, nay? And now we're going to go ahead and plot it. So we're going to plot. I'm assuming you're talking to yourself. Okay. Okay, do we all have our graph of our inverse?
Okay. Yeah.
Okay, so let's talk about the inverse. So the inverse, it also has an asymptote. It also has that boundary line. And that's because if I have a limit horizontally, for the inverse, I'm going to have a limit vertically. So I have an asymptote at x equals 0. I'm going to get as close as I can, but will I ever actually equal 0? No. So this asymptote is at x equal 0. And again, the magic word for the boundary line is called an asymptote. A-S-Y-M-P-T-O-T-E. It's written. Poorly written, but written. This is y equals 0. This is x equals 0. Oh, this is y equals y to the negative 1. And what does y to the negative 1 mean? Inverse. Okay? Graphically, because that's where your asymptote is. That's the name of your asymptote. It doesn't. That's in the invisible boundary line that is never touching. So if you look right here, it's not touching it. It's approaching, but not touching. No, you're good. All right. So let's talk about the domain and range here. Now looking at our inverse, what is the domain of our inverse? It's 0 to infinity. Because now our x's start at 0 and then go to infinity. What's our range? All real numbers from negative infinity to positive infinity. So when you have two functions that are inverses of each other, their domain and range are the opposite. Does that make sense? That's because what did we do to the table? We flipped it, right? We switched our x and our y values. So of course our domain and range have to also flip. Our domain would be x is greater than 0. Okay. All right. Now, when you're looking at it, if you're trying to make sure that you graphed it correctly or you had the right idea, your inverse graphs, they should be symmetrical along what's called your y equals x line. So that the points where y and x, so at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, that is where your line of reflection for inverses is. Or symmetry, whatever. And if the graphs don't have this symmetry, that means they are not inverses of each other. This is our in between, means that they're the same distance from that line. If I could fold it along that diagonal, they should lay on top of each other, right? It's our axis of symmetry for inverses. Or not axis, line of symmetry. It's not an axis. Line of symmetry. Okay. And if they don't reflect over that, then they are not inverses. We know they're inverses because we made them inverses, right? Okay. So table 2 function, looking at the graph that we created, what kind of function is that? It's not quadratic. That is more like a parabola to me. No. Nope. Yeah. Thinking about your do now, what did you use to solve your exponential? Logarithmic. This is a logarithmic function. I did not. So we put logarithmic. Okay. Can you tell? This is the shape of a log function. It's the opposite of of an exponential. How do you solve an exponential? Log. How do you solve a log? Exponential, because they are inverses of each other. And so inverse of exponential is logarithmic. Okay? And because it's a log, that means that our inverse function, would equal log of the same base. What base do we have? What's our base of our exponential? 2. So therefore, this is log base 2 of x is our inverse. So conclusion, what's the inverse of an exponential? Logarithmic, and vice versa. What's the inverse of a logarithmic? Exponential. Can't solve one without the other, even if you tried. Good job. All right. Let's see what happens here. What kind of function are we starting off with? A linear. If you could do log and exponential, you can do any function. So we're starting off with a linear. We're going to choose any numbers for our table. Should we choose big numbers? No, we're going to choose little numbers. -3, -2, -1, 0, 1, 2, and 3. Yes, they're going to become your y values. Exactly. Good job. What he was saying is that if these are our x values for table 1, for our inverse table, they're going to be our what? Y values. All right, how do I find my y's though? Plug it in. All right, what's -3? And then 9 plus 1 is 10. I input -2 and I get what? What's my output? -3 times -3 is 9 plus 1 is. Okay. All right, -2. If I substitute -2 in, what do I get? 7. I substitute -1 in. 4, 0, 1, 2, -4, -5, and 3, -8. So these are the values of my y, right? Now I want to do the inverse. How do I find the inverse? I just gotta switch the x and y. So negative inverse would be 10, -3, 7, -2, 4, -1, 1, 0, -2, 1, -5, 2, -8, 3. Now I'm going to graph and describe their properties. Are we cool with that? Anyone hesitant about plotting the points and describing domain and range? All right, okay. I'm going to be quiet and let you do it. I'm going to do it on my end as well. right? Based on what we got, what is the inverse of a linear? A linear. The inverse of a linear created another what? Linear. Because the domain of all linear equations is all real numbers. Okay. What is our inverse equation? We know it's linear. What the function is linear. What is the equation? What do you need to have for an equation? We need what for linear? Y equals mx plus b. So in this format of y equals mx plus b, we need an m and a b. So what's our slope of our red line? Negative 1/3. Good job. And where does it cross the y-intercept? It actually crosses at 1/3. If you couldn't figure out 1/3 from your graph, you could always just choose any point on the red line and use the slope to solve for your p. Okay? The linear function is the only function whose inverse is the same type of function. For the most part. I mean, rationals can be too. All right, what are your questions about example 2? It's going to always be y equals x. If you graphed it with a ruler, there would be. Yeah. It's going to always be y equals x. So the best way I can show you is using a calculator because it's going to be graphed way prettier than mine. So when I graph negative 3x plus 1, and then we found its inverse, and our inverse was negative 1/3 plus 1/3, right? And then we want to see the symmetry. So that line of symmetry is y equals x. And you can arrow over and you can change it to be a dash, dotted, solid, whatever line you want it to be. So I'm going to make it dashed so you can see it. Now I'm going to hit graph. So there's the first function. There's the second. And then there it is. So can you see how it's a little more even with the calculator? And there is. If I fold over that diagonal, along the diagonal, that symmetry is along the line, that diagonal. Yes, that diagonal is like a fold. Okay? Yeah. So we were supposed to have a class combo about what we saw and what we recognized and what we pulled in together. So in total, let's talk about really quick. Exponential, what's its inverse? Logarithmic, and goes vice versa. A linear, what is its inverse? Another linear. What is the line that we are looking for that reflection? No, line of symmetry. And what is it? Y equals x. Okay. Okay. We will pick up tomorrow.